In Lecture 3, we discussed how two phenomena can be either dependent or independent, and we learned 5 ways to test for independence using probability.
In some situations, it's obvious that two things are related, and we don't need data to tell us that they're dependent. And in other cases, it's obvious that they're independent. But in many cases, it's not obvious one way or the other. For example, let's take smoking and productivity. Are smokers on average more productive, less productive, or is there no difference at all? We can't tell just by guessing. We need data. When two phenomena are dependent, it means they're associated in some way. Changes in one are linked to changes in the other. That means that there must be a mathematical relationship between them that we can quantify or model on a graph. This mathematical relationship could take many forms. It could be quadratic, exponential, logarithmic, or other types of functions. But the mathematically simplest relationship between two variables is a linear relationship. Linear comes from the word line. This means the pattern can be represented by a straight line on a graph. The linear relationship is called a linear correlation. And in statistics, when we talk about correlation, we usually mean a linear correlation. Here's an example of a perfectly linear correlation. Income versus hours worked. Each extra hour you work adds the same fixed amount to your income. Let's say you earn $20 per hour. Every additional hour increases your total income by exactly $20. This creates a straight line because income is continuous. If you work 2.77 hours, then you make 2.77 times 20, which comes out right here. And the same is for every other point. So you get infinite points here, and that creates a perfectly straight line that goes on forever and ever. But such perfectly linear relationships are not interesting. We don't need statistics to describe it. Correlation becomes useful when the relationship isn't perfect, when one variable tends to change as the other changes, but not in a perfectly predictable way. The graph might look something like this. This is when we need correlation techniques to help us find the relationship and measure its strength and direction. When the line goes up to the right, it means that one variable increases as the other increases. So it's a positive correlation. When it goes down to the right, it means that one variable increases, the other variable decreases. So it's a negative correlation. And if the data don't tend to follow a straight line at all, then there's no correlation. The strength and direction, which by direction I mean positive or negative, of the linear relationship between two variables x and y are measured by the Pearson correlation coefficient, which is denoted by the letter R. It ranges between 1 and -1. When it's a perfect positive correlation, it's 1, and when it's perfectly negative correlation, it's -1. This is a formula for R. It's equal to the sum of the deviations from the mean of the x variable times the deviations from the mean of the y variable divided by the square root of the sum of the square deviations of the x variable times the sum of the square deviations of the y variable. So we learned in lecture 1 that the sum of the deviations from the mean is always equal to 0. So this sum itself without this, or this itself without that, would always be equal to 0. So why isn't this 0? That's because we multiply each deviation of the x times each deviation from the y, and then we sum everything up. So if there's no correlation at all between the x and the y, then it will still equal to 0. It wouldn't matter that we multiply one by the other. But if they're positively correlated, then they'll reinforce each other. If they're perfectly correlated, then this whole sum will end up equaling this denominator. So that's why we divide by the denominator to get exactly the number 1 when they're positively correlated. If it's a negative correlation, it works the same way, but with the opposite sign. If you square this r, you get the coefficient of determination, r squared, which is usually denoted by an uppercase r squared. And it's equal to the part of the variation that's linearly explained by the other variable divided by the total variation. So it'll give you the proportion of the variation that's explained by the correlation. And since it's a proportion, it ranges between 0 and 1. It's also obvious that when you square a variable that ranges between -1 and 1, you'll get a variable that ranges between 0 and 1, since all the negatives will become positive.
There's always a probability that the variables in your sample are correlated just by chance. The smaller the sample size and the weaker the correlation, the larger the probability that there's really no correlation, but just by chance your data points ended up looking like there's a correlation. So we always use a t-test to find the statistical significance of the correlation.
It's important to understand that correlation does not equal causation. If you prove that two variables are correlated, that doesn't tell you anything about what's causing it. For example, let's say you've proved that there's a correlation between taking a nutritional supplement and a certain adverse health effect. So you might think that, well, since we proved it correlated, it's obvious that this supplement is causing that adverse health effect. But that's incorrect. And there's always two reasons why that's incorrect. There's always two reasons why there might be a correlation, even though there's not the causation you think there might be. The first reason is reverse causation. So in this example, it could be that the causation goes the other way around, that people are taking the supplement because they have that adverse health effect. The other reason why there might not be the causation the way you think it is there might be a third variable that's causing both of these effects. So for example, when you find the correlation between taking the specific nutritional supplement and some adverse health effect, it could be that people who take this supplement tend, on average, to do many other things differently than the rest of the population. They're health-minded, let's say, and they take all kinds of other supplements and do all kinds of other things. And maybe one of those other supplements that they take is causing this adverse health effect. So the only way to establish a causation is with randomized controlled trials. But if you don't have randomized controlled trials, there's mathematical tools that could be used to build up a case for causation that I mentioned here in the end of the slide. So let's do this example. Suppose a researcher finds a negative correlation between consumption of sweet potato and eyesight within some population, we'll call X. And this is completely made up, so don't worry about sweet potato. A, explain what the researcher's findings mean. B, do the researcher's findings imply that consumption of sweet potato negatively affects eyesight? Explain. So for A, the answer is simply that the negative correlation means that as consumption of sweet potato increases, eyesight tends to get worse. Now, does this mean that the sweet potato is causing this? No, the answer is no. We know that correlation is not equal causation. So as we explained, there could be two possibilities. It could be that for some reason people with bad eyesight tend to eat more sweet potato because of the bad eyesight.
Or it could be that people who eat sweet potato tend to do other things too, and one of those other things is bad for the eyes.
The next question is, does the data below seem consistent with the researcher's finding? Explain what the data seems to show. So this is the average ounce of sweet potato per day, and this is the level of eyesight. Does more sweet potato tend to show a lower level of eyesight? Well, if you focus only on these 3 points, then yes, it's very little data, but it would seem to show a negative correlation. But overall, it does not show that because these two points are not consistent with it. And if it would only be these 3 points, then it would show a positive correlation. But all 5 points together show no correlation. The R value, the Pearson correlation coefficient, tells you the strength of the correlation, and whether it's positive or negative. It doesn't give you an exact straight line through the data that you can use to predict what the Y value would be for different X values that are not in the data. That's done by regression. The x variable is always called the independent variable, and the y variable is always called a dependent variable. So how do you guess the best straight line through the data? Suppose you draw this line at the mean of the y values. So we're completely ignoring now the x values. We don't care where the data is on the x-axis. We only care where they are on the y-axis. In other words, how high they are from the bottom to the top. So this is the mean. Now, if we take all the deviations from the mean, that means we add up these 5 values, this plus this plus this plus this plus this. Then we know from lecture 1 that, as we mentioned earlier, we're going to get 0. So what do we do when we want to know the sum of the deviations from the mean? We just square it. So we get the square deviation from the mean. So if we sum up this squared plus this squared plus this squared plus this squared plus this squared, we're going to get the sum of the square deviation from the mean. And that's going to be some pretty big number. What if instead of taking deviation of the mean, we turn the line through all the points like this, and now we take the sum of the square deviations from this line? Obviously, this sum of these square deviations will be much smaller than the sum of the deviations from the mean, because the line went right through all the points. So this is essentially the technique that is used. We're not going to go into details about it, but this is the technique that's used to find the line of best fit, to predict what the line is when we're estimating that the data follow a straight line. In other words, we find a line that has the smallest sum of squared deviations from that line. So every straight line, this is just general algebra 1 from like 8th, 9th grade. Every straight line is a graph of the function y equals the y-intercept plus a slope times x. So whenever we talk about this kind of line that we make up based on some data that we predict what the line is, we use y hat. So y hat means we're talking about this line that we're making up, that we're predicting. Now the y-intercept always means the value of y when x equals 0. So in this case, the y-intercept would be, let's say, 1.5. Let's say if this is 1 and this is 1.5. So we see the line goes right through 1.5 at x equals 0. So the y-intercept will be 1.5. And the slope just means how steep this line is. And the way you calculate it is you take any 2 points on the line and you do the change in the y divided by the change in the x. So in this example, the 2 easiest points to see would be this point here, which, as you can see, is 6, y is 6 and x is 3. And this point here, which we already said is x is 0 and y is 1.5. So if you do the change in the y, that would be this minus this. So that's 6 minus 1.5. So that would be 4.5. And you divide that by the change in the x, which is 3 minus 0. So you have 4.5 divided by 3, and that's equal to 1.5. So we get, for this equation of this line, would be y hat, again, it's hat just because it's a line that we are making up based on the data, equals 1.5, that's the y-intercept here, plus 1.5x. So the slope is 1.5. The slope is not 1.5x. The slope is just 1.5. The equation is slope times x. And what the slope tells you is the rate at which y changes for every unit change in x. And then one more thing you should know is that the residual means the observed y value minus the predicted y value. So for every point, the residual will be what we observe minus the point on the line. So for example, for this point, this the residual is 2 minus 1.5, it equals 0.5. And for this one here, since the point is under the line, you can see it's going to be a negative number. And let's see, if this is 5, if this point is 5, then it will be 5 minus 6 equals a negative 1. So if we look back at the income versus hours worked, these points don't have any residual because this is a perfectly straight line. So all the residuals are 0. And the equation for this line, let's say if all you have are these data points and you're just predicting the line based on these data points, it will be y hat equals 20x. So the slope is 20. And what about the y-intercept? That's 0, right? Because when x equals 0, y equals 0. Because in this case, we're talking about getting a $20 salary per hour. That means if you don't work any hours, you get 0. So the y-intercept will be 0. So if you write it out explicitly, it will be y hat equals 0 plus 20x. But that's the same as y hat equals 20x. Now let's say you moved up this whole line by, let's say 25. Here, let's say it would be parallel to this line, but it would go from 25 all the way up like that. Then that means it would still have the same slope, but the y-intercept would be 25. So the equation would be y hat equals 25 plus 20x. And the interpretation would be that this person gets $25 even if he doesn't work at all. And then from then on top of that, he gets $20 per hour. But he starts out with just like a gift of $25. So let's do an example. A researcher collected data on the number of hours students studied, which we call X, and their test scores, which we call Y. The regression analysis produced the following equation for the line of best fit.
Y hat equals 45 plus 3.2x.
So what is the independent variable and what is the dependent variable? Well, the answer is the independent variable is always X, which in this case is the hours students studied. And the dependent variable is always Y, which in this case is the test scores. And intuitively, this makes sense. The test scores are what depend on the hours studied, not vice versa. But how is this consistent with the principle that correlation does not imply causation? The researcher studied whether and by how much more study tended to coincide with higher test scores. She presumably didn't conduct any randomized controlled trials or even do any mathematical techniques to specifically study the causation. And although in this case the most sensible explanation probably is that the studying causes the increase in test scores, that's not the only possible explanation. It could be possible that students who studied more did so because they enjoyed it, because they were already good at it, or because they had better access to resources, which might be the real cause of their higher scores. So why do we always call X the independent variable and Y the dependent variable if we're being neutral about causation? The answer is that when we say Y is dependent on X, we only mean that Y is a function of X. We're trying to describe and predict Y based on X. We're not implying actual causation. Okay, B. What is the y-intercept? What is the slope? And what does each of them tell us in terms of the researcher's findings? So the answer is the y-intercept is 45. And what that tells you is that according to this mathematical model, a student who studies 0 is predicted to get a 45 on the exam. And the slope is 3.2. Again, it's not 3.2x, it's 3.2. And that tells you that for every additional hour, for every hour a student studies, they get another 3.2 points on the exam. C. What test score would these results predict for a student who studied for 6 hours? So you simply plug in 6 instead of x, and you do 45 plus 3.2 times 6. And if you put that in the calculator, you get 64.2. So that's the answer. D. A student who studied 6 hours actually scored a 70. Calculate the residual. So the residual is 70 minus 64.2, which is equal to 5.8.